Hello everyone. For centuries, light was seen purely as a wave capable of interference, diffraction, and polarization. But when the photoelectric effect was discovered, it revealed something astonishing. Light can also behave like a stream of tiny particles. Einstein called these particles quanta of light. Today, we know them as photons. Each photon carries a definite amount of energy proportional to its frequency. So rather than a continuous wave of energy, light is actually made of countless photons, each hitting the metal surface one by one, just like bullets striking a target. Einstein's idea gave rise to a simple yet powerful equation describing the energy of a photon, E equals h times nu. That is, energy E equals Planck's constant h multiplied by frequency nu. Here, Planck's constant h equals 6.626 times 10 raised to the power minus 34 joule-second, and nu, the Greek letter nu, is the frequency of light in Hertz. Now, for the photoelectric effect, this energy must help an electron escape from the metal surface. Some of the photon's energy is used to overcome the work function of the metal, denoted by the Greek letter phi naught, and the rest becomes the kinetic energy of the emitted electron. So the energy balance equation becomes nu equals phi naught plus k max. Let me repeat that carefully. Planck's constant h multiplied by frequency nu equals the work function phi naught plus maximum kinetic energy k max. The electron will only be emitted if h times nu is greater than or equal to phi naught. If that condition isn't met, the photon simply doesn't have enough energy to free the electron. From this, we can define the threshold frequency, nu naught, as nu naught equals phi naught divided by h. That is, the minimum frequency required for photoemission equals the work function divided by Planck's constant. This single equation explained every feature of the photoelectric effect. The kinetic energy of emitted electrons increases linearly with frequency because k max equals h nu minus phi naught. No electrons are emitted below a certain threshold frequency even if the light is intense. The intensity of light affects only the number of electrons emitted, not their energy. And emission is instantaneous because one photon transfers its entire energy to one electron instantly. Now, we can express this relation in terms of the stopping potential used in experiments. We know that the maximum kinetic energy of the emitted electrons equals the charge of the electron multiplied by the stopping potential. That gives us k max equals E times V naught. Substitute this into Einstein's equation, nu equals phi naught plus E times V naught. Rearranging, we get EV naught equals h nu minus phi naught. And dividing both sides by E, V naught equals open bracket h divided by E close bracket multiplied by nu minus open bracket phi naught divided by E close bracket. Let me read that clearly. Stopping potential V naught equals Planck's constant h divided by electronic charge E multiplied by frequency nu minus work function phi naught divided by E. This tells us that if we plot V naught on the y-axis and frequency nu on the x-axis, we get a straight line. The slope of that line equals h divided by E. And the x-intercept gives us the threshold frequency nu naught. In 1916, Robert Millikan decided to test Einstein's photoelectric equation. At first, he didn't believe it. He thought light couldn't possibly act like a particle. But after 10 years of precise measurements, he found something incredible. When he plotted stopping potential V naught against frequency nu, the line was perfectly straight, and the slope gave the value of Planck's constant 6.626 times 10 raised to the power minus 34 joule-second, exactly the same as that obtained from Planck's theory of blackbody radiation. Instead of disproving Einstein, Millikan's experiments proved him right beyond doubt. He went on to receive the Nobel Prize in 1923 for this very work. So, what exactly are these photons? Let's list their fundamental properties. Each photon carries energy E equals h times nu, and since the speed of light c equals frequency nu multiplied by wavelength lambda, we can also write E equals hc divided by lambda. Spoken clearly, energy E equals Planck's constant h multiplied by speed of light c divided by wavelength lambda. Now, photons also have momentum, even though they have no mass. The momentum of a photon is given by P equals h times nu divided by c. We can simplify that using c equals nu times lambda, giving P equals h divided by lambda. That means the shorter the wavelength, the greater the photon's momentum. All photons of the same frequency have the same energy and momentum, so increasing light intensity only increases the number of photons per second, not their individual energy. Photons are electrically neutral. They always travel at speed c equals 3 times 10 raised to the power 8 meters per second, and they are not deflected by electric or magnetic fields. Now, what happens when photons collide with particles like electrons? In a photon-electron collision, both energy and momentum are conserved. However, the number of photons may change. One photon can be absorbed, or new ones can be emitted. This was spectacularly confirmed in Arthur Compton's 1924 experiment, where X-rays scattered from electrons changed wavelength, a phenomenon called the Compton effect. The Compton shift proved that photons carry momentum P equals h divided by lambda and interact with electrons just like real particles. To wrap it up, the photon theory of light tells us that radiation behaves as if it is made up of individual particles, or photons. Each photon carries energy h times nu and momentum h divided by lambda, travels at the speed of light, and is electrically neutral. This dual nature, light behaving as both a wave and a particle, lies at the very heart of quantum mechanics. Einstein's theory of the photoelectric effect won him the Nobel Prize in Physics in 1921, and Millikan's precise experiments later confirmed it.